12-8. Don't be surprised if I pause once or twice through this one. It's kind of long, and I gotta sometimes go back and get my train of thought. But we're talking now about comparing more than two variables, right? We've in the past compared to two and used some z's and t's and those types of things. But what do we do if we have more than that? Okay. Well, here's what we do. So we state a hypothesis, or a null hypothesis, is that they're all equal, that mu sub 1, mu sub 2, and mu sub 3 are all equal. And our alternate hypothesis then is that they're not the same. Okay, and we're going to reject it if f is greater than 4.26. And how do we find that? Well, we find our numerator and our denominator, and our numerator is k minus 1. So that's our number of treatments. Okay, in this case we're going to call it treatments. You can call it columns, whatever you want to call it, I guess. So that's 3 minus 1 is equal to 2. And then our denominator is our n, our total size of the sample, if we want to call this a sample, but our total number of whatever items that we have in there, minus the k, or the 3 columns, right? So that's equal to 9. And then you look in the back of your book, and I should look. I haven't looked for an F distribution online. I probably should, but in your back of your book, it's page 736 or 37, depending on what you have in terms of the significance. And for our problem, I think for 7, the significance level is 0.05. Your guys' 8 is 0.05 as well, so we just look at page 736. Our numerator is 2. Okay, and our denominator is 9, and so you go down that column, the number 2 column, until you get to 9, and you get to 4.26. So that's where you get your F value, okay, that we're looking for. And what we're going to do is when we get all our calculations done, if our F value exceeds that 4.26, then we reject our hypothesis, null hypothesis, that they're all equal. And how do we do that? Well, I'm going to show you the long way to do it, because it's so much fun, and I know you guys will enjoy this, and I do want to see you guys do it the long way on your assignment for number 8. Okay, well, let's get our data first. So we've got our data for 7 is that we've got the 3 columns, or the 3 treatments, okay, and we call it that, and we've got our data. Well, what we have to do now basically is find a mean of all that data, okay, and I've done it this way because I want to find first the total, okay, so I've just summed each of sum right of that one, okay, and I sum all of those, okay, and then I want to count, and this will be more important for you guys because you've got different numbers, okay, in each one. Okay, but I'm going to go ahead and count. Let's delete that, and I'll show you how to use the count function. So we come up and we just hit count, okay, and I want to count this right here, okay, and that's all I got to do. So that counts the number of them in there, and yeah, I could have counted them by myself and put it down there, sure, but it's kind of nice to do that, right? And then I just divide, my sum divided by my count to get my average for each column, okay, or for each treatment. It's 33 divided by 4, and again I can drag that down, okay, and now I can either I can do this a couple different ways, right? So I can take all my totals here, okay, so I'll just do a sum of that, boom, and then I sum the total of my count, so I know the total number of items that I have, right? And then I can simply divide the 61 by the 12, right? Is equal to my total there, divided by the 12. And there's other ways you could get that. I mean, you could do a sum of all of these and then just divide it by the count of all of these and whatnot. But it's kind of nice to have these because I think we're going to need those a little bit later. Well, now what do? Well, now we go through, and actually what we want to do is find the variance of all of these from our mean, right? And it's really no different than think of all these if they were just in one column. All three treatments were in one column, right? And then this was our mean. Well, how would we go about doing that? It looks different the way I have it set up here because you know, it's 3 columns and 4 rows. It looks a little bit different, but it's basically the same thing, right? All we do is take each number and subtract it from, or subtract our mean from it. And again, you can do it either way because we'll square those and that'll get rid of the negative sign. Okay, in this case it looks like I've subtracted the mean from that, and so I simply have to go, this is equal to my number minus my mean, and I want that mean, the reference to that, to stay the same, so I'm going to use my dollar signs and I'll hit enter. And I can just extend this thing. Looks like I can only go across and then I can go down. Okay, and that's simple. And then I have to square it, right? So same thing. I can simply say this is equal to, you know, this number. It's probably the easiest way, just to use my 6. I could use the square function. I think there's a square function. It's easier to do it this way anyhow. Okay, and these references are all going to stay the same. So once again, I can drag it over, and then I can drag her down. Okay, and then I sum all of these, right? And that gives me the variance of each column. Okay. And we basically we're using the population variation, or variance, and also the population standard deviation. If we find it, I don't think we ever find the standard deviation. I don't think we need that, but you know, we would take it -1 if we thought it was a sample, but we're using the population. Then this is my overall variance of all of these. Again, if these were all, you know, lined up, you know, all I'd have to do is sum that, and I would get my overall variance. But I've taken the variance of each column, or the total of each column, I'm sorry, and then if I total those up this way, I will have my overall variance. Okay, that then ultimately what we're going to prepare is called an ANOVA table, right? And you can see some of those. There's one that's ANOVA single factor in the middle of page 393. There's one there also on the bottom of page 392, and in the blue spaces on kind of 390 and 391, right? So ultimately that's going to be put into my total here. Okay, now that's my total variance. Okay, but I also got to get the variances for each column, basically, is what I'm going to do here. And so I've got a mean. That's why I did it this way. I've got a mean for each column, right? And to get the variance, then I just take my, you know, my each individual one, subtract it from the mean, or subtract the mean from it. Okay, and that's what I'm going to do down here. So this is equal to this one minus my mean, which again I want to use my dollar signs, hit enter, and I can drag this down. Okay, kind of why I set this up, you know, these ones straight across from there, because then the references stay nice, and this one straight down from there, the references also stay nice. And so I can do the same thing. I should then just be able to carry this over. Oops, I guess not, because I had my dollar signs in there, so let's not do that. Okay, so this one then is equal to this one minus my mean, and then use my F4. Okay, and I would drag that down. I'll do the same for that last column, so I have to do each column, right? And then I come over here and I do the squares, equal to this one squared. Boom. This one I can't. I should be able to just drag it over and then drag it down. Okay, find my totals and my total. Okay, and we end up calling that the error. Okay, so these well, I do have that as a sum there, but these then become figures that we're going to use in figuring out that ANOVA, right? So I've got the total here. The SS stands for the sum of the squares. Golly, sum of the squares. So how do I get that? Okay, well, I get that by taking my total variance here, okay, the sum of the squares, that's what this is, right? My total sum of the squares, and subtract my error, okay? What I've calculated here is my error for the sum of the squares to get the treatments, okay? So it's kind of an adjustment factor or whatever, and it gives us the treatments, okay? So I did that in this particular one. I kind of created a separate space for it, and I just said this is simply equal to my total minus my total, okay, for the columns. And then I put that in here. This is simply equal to this, and the errors is equal to this. Okay. And then I can total that up. I can also just take this one and reference that. Either way you want to do that's fine. Okay, my degrees of freedom, remember I had up here, I've got my numerators 2 and my denominators 9, so I put my degrees of freedom in. Okay, I don't like those underlined like that. I'm going to get rid of that and instead underline the, there you go. Okay, so my degrees of freedom, 2 and 9, so my total degrees of freedom are 11. Okay, then I got my mean of the squares, right? My mean of the squares is simply my sum of the squares here. Sum of the squares of the treatments divided by my degrees of freedom. So that's simply equal to this divided by this. This all becomes kind of important a little bit later. Okay, and it's likewise here. Okay, so I can actually drag that down. Okay, and then my f value, that's what I'm ultimately looking for, remember, is f is simply equal to this one divided by this one. Okay, so equal to my mean square of the treatments divided by the mean square of the error. So my f turns out to be 21.9. Okay, and I guess I had some instructions there. Divide my MST, or mean square of the treatments, by the mean square of the E, by the error. Okay, so I end up with an F of 21.94. So what's that mean? Is that greater than my 4.26? It is. So I'm going to reject the null. Okay, that they are not all equal. They are definitely not all equal. Okay, oh, look at that. How'd these numbers down here turn out to be just like my numbers that I created there? Oh my goodness, is there an easier way to do this? Heaven forbid. We'll just have to go and see. Okay, we'll just have to go and see. I'm gonna delete this. I'm gonna get rid of my borders there. Okay, because I want it to look nice and fresh. What was that? An ANOVA, what did it say? ANOVA single factor. Again, we got to go to our data, make sure that you've enabled that or those add-ins. So I go to my data and I go to my data analysis, my ANOVA single factor, okay, and my input range. I'm going to include my labels here, okay, but it's grouped by, in this case, my treatments are columns. Okay, had my treatments been over here, if I was going this direction, okay, then I would change it to rows, but in this case it's grouped by columns. Okay, and so I'm going to go ahead and click this so I get the labels. My significance is 0.05, that's what it calls for, so I don't need to change that, but you might if yours was different. Okay, and then my output range is, I'm going to kind of highlight that and make that my output range there, and that's the same as what I had. Looks good. I hit OK. Okay, so I want you to do this one to prove to me that you came up with the right answers up here. Okay, but I do want you to go through this on yours. Okay, so you get to do it the long way and get to show me that you got skills of figuring out your variances and all those other things. This also gives me a p-value extremely small, which again means that it really supports my conclusion, you know, that those means are different, because it's really small. And it gives the F critical, which, you know, we got 4.26, you know, using the table, rounds it off a little bit. It calculates for us at 4.25649, so you round it. Okay, but everything else is the same. We came up with the exact same numbers doing it the long way. So have a little fun with that. A lot of math and good use of Excel, etc.